Okay, so hybridization. So hybridization basically follows right on the heels of VSEPR theory. Now, it's used in essentially all second year textbooks. And it basically grew out of the premise that if you're using p orbitals and s orbitals, like in the case of carbon, you've got 3 different p orbitals and an s orbital, and yet methane was tetrahedral in structure. And it wasn't really easy to visualize how you get a tetrahedral structure using those orbitals like visually. So they came up with hybridization. And it's nice because it makes things easy to visualize, but it isn't necessarily correct. If you take Dr. Yan's class on group theory, you're going to see how you can construct all of the molecules that we're constructing using the orbitals, basically the s and the p orbitals. So there is a way of doing it. It's just slightly more complicated, and that doesn't make our lives any easier with regard to getting everyone up to speed on sort of stuff. So it's ubiquitous, which means it's everywhere, but it's not particularly accurate. Okay, so how it works is that, and because we're dealing with carbon, the valence electrons, of course, on carbon, if you draw the lowest energy electronic configuration, would be a 2s orbital and the 3 different, maybe I'll get up my little laser pointer here. The 3 different p orbitals that have got directionality in the x-axis, y-axis, and z-axis. And what you do is that you mix them or you hybridize them. So you start with these 4 orbitals. And remember, the s orbital would be lower in energy than the 3 p orbitals. You mix them all and you come up with 4 new hybrid orbitals. And we call these sp3. So it starts with an s and it's got 3 p's, so s and then the 3p. You start with 4 orbitals, you end with 4 orbitals. And when you mix these orbitals, let me see if I can go into my other screen. Going to the whiteboard here. Am I drawing? Yes, I'm drawing. Okay, so if you've got an s orbital, which is round, and you are mixing it with a p orbital that has got 2 phases, when the s orbital mixes with the phase that it matches, that lobe, darn it, that lobe is going to get bigger because they are in the same phase. And the lobe which it would be mixing with on the other side is going to get smaller because it is opposite phase. And so one lobe is used for bonding. I don't know if you can see this. Can you see this?
Yes, we can.
Okay, thank you. All right, good. One lobe is used for bonding, the one which they're in phase and it gets bigger, and I've kind of drawn this long, it's actually longer. And then the lobe, which is the other color, this is what we would call, this would be in the molecular orbital theory type of things, this would be the anti-bonding lobe. So this is where these hybrid orbitals come from. And so in the case of so the bonding lobe is elongated, and if you read textbooks, they'll tell you, here's the 5 reasons why orbitals would hybridize, all very logical. But you've got this larger bonding lobe, and it can provide better directionality when you're making your molecules. So when we've got methane, carbon is going to be using its sp3 orbitals to make these sigma bonds. So I guess one of the take-home messages for hybridization is that hybrid orbitals are used to make sigma bonds. So sigma bonds are for hybrid orbitals. So this carbon has got how many sigma bonds associated with it? Well, it's got 1, 2, 3, 4. Let me use my little laser pointer. It's got 1, 2, 3, 4 bonds, 4 sigma bonds. So that means it's going to need 4 hybrid orbitals. So when we're talking about sp3, it's got, you just can count them up, 1 and then 3 is 4. So anytime you see carbon with 4 bonds, sigma bonds, it's going to be an sp3 hybridized carbon. And this is going to correlate to a tetrahedral structure because you got these 4 sets of electrons and they want to be as far away from each other as possible, which would be a tetrahedral structure. Does that make sense? Okay, so let's go to the next slide here. Now, when we did our little section on VSEPR theory, we said that double bonds equaled triple bonds, which equaled sigma bonds. So they all had the same repulsive power. And that might not make any sense. And this little next section will hopefully clarify this. So if you've got any type of double bond or triple bond, you need, remember, double and triple bonds are made with, they're not sigma bonds, they're pi bonds. And you can only make pi bonds with p orbitals. So pi bonds will have the sideways overlap of electron density. And so for those types of systems, you need some p orbitals to make these double bonds or triple bonds. So in the case, anytime you've got a double bond, that means you need a p orbital, which means that it can't be sp3 hybridized because you need a p orbital, not a hybrid orbital. So in the case of sp2 orbitals, what happens is they mix an s orbital with 2 p orbitals to make 3 new hybrid orbitals, which are the sp2 hybridized orbitals. But we started with another p orbital, and that one's left behind, and so it's kept over. So it's basically carried over. So after hybridization, you'll have 3 new hybrid orbitals, which are all sp2. And these orbitals will be used to make sigma bonds. This p orbital will be used to make pi bonds. Now sp2 orbitals, again, they're elongated much in the same fashion as an sp3, except for this lobe isn't as big, and this lobe is slightly larger. It's similar, but it's just not as elongated. So these sp2 orbitals are going to be used to make sigma bonds. So if you've got 1, 2, 3 sigma bonds, and they are trying to get as far away from each other as possible, the geometry of that system will be anybody?
Trigonal planar.
Right, great, wonderful. Yes, so you've got 3 sets of electron pairs. They want to be as far away from each other as possible. So I've drawn this really poorly. They will be 120 degrees. 120 degrees. So these would all be sigma bonds. They are all made with the hybrid orbitals. Your p orbital, if we're looking at this from above, is going to be here, and it's going to be double bonded to in some direction here. So an example would be, which is on the next page. Come on. I want to stop this. So an example of this is ethylene. Okay, so I've tried to draw this so that each of the, oh, look at that, all that stuff carried over to the other page. How sad. Okay. Let's close this first. Okay. Right, so with ethylene, I've tried to draw this in a fashion that, so all of the sigma bonds are in black and the blue bond is a pi bond. So the black sigma bonds are going to be, we're going to be using sp2 hybrid orbitals for those. Of course, hydrogen's orbital that it uses to make bonds is the 1s, so that's why we put 1s there. But this blue bond is a pi bond, and so that's used with the remaining p orbital. So if we draw this from the side, the electron density from one lobe, which would be in phase, we could shade this if we wanted to. Shade that. Whoops. So these would be in phase and electron density would be shared there. Electron density would be shared here. This is the sideways overlap. So the 1, 2, 3 sigma bonds would all be as far away from each other as possible, which would be 120 degrees. And this would be trigonal planar. And the p orbitals would have the sideways overlap to make the pi bond. So that's basically how an sp2 orbital works. So we will have 1, 2, 3 hybrid orbitals making sigma bonds, and the leftover p orbitals would make the pi bond. I better erase this. Okay, so the key points, sp2 carbons will be trigonal planar. Pi bonds use hybrid orbitals, sorry, sigma bonds use hybrid orbitals, and pi bonds use the p orbital. And the other important part is that this p orbital, if we're gonna do a visualization here, the p orbital is 90 degrees from the plane. So this is perpendicular to the plane, which would be along here. These would be 90 degrees from that. So they occupy a completely different space. So that would be the key point for. So anytime you see carbon, which has got one double bond, it will be sp2 hybridized. And last but not least is the SP system. So in this case, we're mixing one s and one p to make two new hybrid orbitals, which will be sp hybrid orbitals. And you've got two remaining p orbitals that are going to be used to make pi bonds. The diagram of this is similar as before, except for this lobe is getting smaller and smaller and smaller. And it will be 50% S, 50% P, because one S and one P went to make it. Whereas an SP2 would be 67% P and 33% S. And if this is, of course, going to be used to make triple bonds. It's a little bit more difficult to draw this, but I did my best. So acetylene is very similar to the example I had in the question. We talked about the geometry at a carbon like this. So this would try to get as far away from that. So that would be 180 degrees. So hybrid orbital, hybrid orbital, and the two B's would be the pi bonds. So the two p orbitals are 90 degrees different from one another. So one is in the plane of the sort of this whiteboard going straight up and down, whereas these, the green ones, are sort of, one lobe is pointing directly towards us and the other lobe is pointing into the background. So the electron density would be above and below and on each side of this, of the various carbons. So this would be a linear molecule, sort of like a cylinder, but this p orbital would be 90 degrees from this p orbital. Any questions on that at all? So the summary for basically for hybridization is, if you can count 4 sigma bonds, it'll normally be sp3. So with carbon, it's going to be sp3. We're going to show you some examples in a second about when nitrogen or oxygen, when they actually break this little rule here. But for carbons, if you can count 4 sigma bonds, sp3 hybridized. If you've got a system where you've got 1 double bond, so in ethylene, or if you've got an empty p orbital, which would be a system like boron trifluoride, or if you've got, say, here, this nitrogen, this is an imine. We're going to see this in the inorganic too. So we would have hybrid orbital, and these lone pairs would be in a hybrid orbital. And then the remaining would be a p orbital using, sorry, a pi bond using a p orbital. So those are basically the systems here. Like the Y could be 2 sets of electrons. If you take group theory, Dr. Yan's going to show you how this oxygen, these 2 sets of lone pairs are actually not the same. But that's for everybody who's taking group theory later on, next term. Well, the joys. Okay, and then last one would be, we've got Z and 2 sets of p orbitals. So this means that we have got a triple bond or 2 double bonds. So triple bond, single bond, acetylene is a nice example of this. Triple bond and lone pairs. Well, here is a nice little molecule. The nitrile group here. And then Z with double bonds on either side. This is a special version. This carbon here, because it's got 2 p orbitals, or sorry, 2 pi bonds made with p orbitals, it has to have a system like this. They have to be, this carbon here, one set will be in the plane of the board and the other one would be coming towards us. So this is a really special sort of structure for carbon, in the case of carbon, but these will all be linear or sp hybridized. So 1 set of bonds, the hybrid orbitals to make the sigma bonds, the remaining use p orbitals to make the pi bonds. So if we go back to that same molecule we had before, we should be able to figure out what the hybridization of each is. And so it's gonna match that in Vesper theory, if linear structures should be sp hybridized, tetrahedral structures. Okay, 15 more seconds. So what do we have? Blue, SP. Green, SP2. Yellow, SP3. And that is correct. So this blue carbon has got, let me see if I can get my little laser pointer back. Okay, well, okay, so this blue carbon here, we've got 1, 2, this bond here is a triple bond. So one of these bonds will be a hybrid orbital. So hybrid orbital, but the other 2 bonds have to be made with p orbitals. So there's only 2 hybrid orbitals here, so that means that this has to be sp. We've got, because we need those p orbitals on this carbon to make the double bond, and then consequently after that the triple bond. So this will be sp hybridized. Likewise, the green carbon here has got 1 double bond, so that double bond will be made with a p orbital. So that means that these remaining 3 sigma bonds have to be made with sp2, because there's 3 bonds left, s, and then 2 p's, 1, 2, 3, comes up to 3, so sp2. And then last but not least, this carbon here has got 1, 2, 3, 4 sigma bonds. So to have 4 sigma bonds, you need an sp3 hybridized orbital, because an sp3 hybridized orbital, there's 4 of them, and you've got 4 sigma bonds. So hence this will be sp3. Good, excellent.